The greatest physicist between Isaac Newton and Albert Einstein was James Clerk Maxwell, who, in the middle of the 19th century, organized everything that was then known about electricity and magnetism into a single coherent theory, and then advanced that theory a tremendous leap forward. So here's what was known at Maxwell's time, although he would have kind of organized it into this format. Gauss's law was known, which tells us how electric charges generate electric fields. The no monopoles law was known, which tells us that there are no magnetic monopoles and all magnetic field lines are closed loops. Faraday's law of induction, that tells us how a changing magnetic field produces an electric field. And then Ampere's law, which tells us how an electric current produces a magnetic field. So Maxwell kind of organized all this information here, took a look at this set of ideas, and felt somehow that something was missing. We have here two equations, the first one and the fourth one, that tell us how sources generate fields. Electric charge can be considered the source that generates electric field. Electric current can be considered the source that generates magnetic fields. So we have these two source equations, but then there's this odd one, Faraday's law, which tells us how a changing magnetic field produces an electric field. And Maxwell felt that although no one suspected at the time that these equations were somehow incomplete, that there was some additional effect here that had never been noticed in experiments. And he proposed that there was indeed an additional term here on Ampere's law. He felt that there was an asymmetry in the equations that needed to be corrected. He felt that if a changing magnetic field, as represented by this rate of change of magnetic flux, if a changing magnetic field could produce an electric field, then perhaps a changing electric field could produce a magnetic field. So he proposed on these theoretical grounds, this sort of hypothesis based on an idea about how this all ought to fit together. He proposed that there would be an additional term added to Ampere's law. That in addition to magnetic field being created by electric current, that a changing electric field should produce a magnetic field as well. So he added this Maxwell term over here, that the time rate of change of electric flux through an open surface should also generate magnetic field, just as electric current generates magnetic field. So this is the time rate of change of electric flux through some open surface. Maxwell was proposing to put electric field and magnetic field kind of on equal footing by restoring this symmetry here. And based on this proposal, he then imagined an experiment that could be done to test whether this equation was accurate. He imagined what phenomena would result if this term really was present. And subsequently, experiments were conducted to verify that this is indeed true. The term that Maxwell proposed was verified afterwards by experiment. So it's one of the rare and great instances in the history of science where the theory came before the experiment. Normally, an experiment observes something, then we try and come up with an equation to explain what we observed. In this case, the opposite happened. Maxwell felt that this term ought to be here to complete the theory, and then it was afterwards verified experimentally. And so this fourth equation, because of this Maxwell term here, is known as the Ampere-Maxwell law. Here's the Ampere part, the current producing magnetic field, and then here's the Maxwell part. And now our set of four equations is fully complete. This is Maxwell's complete set of equations for electromagnetism. This is the complete theory of electromagnetism. This tells us everything there is to know about electric fields and magnetic fields, what generates them and how they're related to each other. It's the complete classical theory. The only thing you would need to add to this in order to understand electromagnetic phenomena is the equation that tells us how these fields affect particles. These equations tell us how particles generate fields and how moving charges generate fields and how changing fields generate each other. But we need to know how the fields affect particles. To that, we need to add in the Lorentz force law here. The electric force plus the magnetic force on some point charge. We could sort of combine those into a single combined electromagnetic force, and we call this combined electric plus magnetic force the Lorentz force here. So Maxwell's equations tell us how the fields are generated, what their shapes and geometries are, how they relate to each other, and then our Lorentz force law here tells us the effect that those fields have on particles, on charged particles. And that is our complete classical theory of electromagnetism.